多少？教练讲话，给他听。Yeah.做的。这是什么？油。
So I want to take off some of the pressure and not give you extra problems today, but that means it's up to you to tell me what to do. So if you have any particular topics you'd like me to cover, I'll go over them. So any suggestions about something, any problems in the lecture notes, any questions on lecture notes, any questions about problem sets, the last year's final, last year's mock, anything you want me to go over, I'll go over it in some detail. Yes, ma'am?
Well, the GTFP measures with the intermediate inputs and without, not really the mechanics, because I think those are quite clear, but the intuition behind how the GTFP with just find demand is being, I mean, how this can be interpreted as a measure for the GTFP opposed to the other one with intermediate inputs. It's not quite clear to me how this relates.
Okay. Give me more guidance. So what what?
So if I look at the GTFP measure, where we just compare the growth of output opposed to growth of input.
Okay.
That's the first one. And I'm not quite sure if in this economy there's interrelation between the sectors, so there are also being intermediate goods, if this will be a distorted measure for GTFP or not.
Ah, I see. You want to know the sort of the PPF approach. You're asking. You're asking.
Yeah, that's the right. That's
you're asking about gross output versus value add, or you're asking PPF approach versus Harrod-Domar weighted?
What was the first one again? Sorry.
So one is we have two. So we have a few concepts of TFP. Let's just go over them all. Let's first of all talk about one sector alone. Okay. We have TFP. One sector. We have Q is F of K, L, and M. Okay? And we have value added is some G of K, L. And we have G, Q, T, F, P. Which is GQ minus elasticity K, GK, minus elasticity L, GL, minus elasticity M, GM. And we have G value added TFP, which is G value added minus elasticity K, GK, minus elasticity L, GL. And And maybe, so that we don't confuse ourselves, we should put little q's up here. It's the elasticity of q with respect to k, l, and m. And this is the elasticity of value added with respect to k, l, and m. Okay? So this is the one sector. I'm going to come to your PPF thing in a second. And we know from this that the big result is G value added TFP is equal to tau GQ TFP, where tau is equal to price of Q over price value added. Okay, so that's one result we have. This is the big result that we have there. Then we have TFP multi-sector. PPF approach. GTFP is equal to summation across I, theta I, GYI, minus summation K, alpha K, GJK. And YI equals final demand for I. JK equals factor input. And this is theta I is share of final demand and alpha K equals share of income. Okay, so this is the PPF approach. And then we have,
Can I just ask a question?
yes, sure.
So if we take the PPF approach, but we have intermediate goods, would this be a distorted measure of GTFP or?
No, I was going to answer your question. It's the correct measure of TFP. It's the correct. So by using final demands as opposed to outputs, this is the key thing. By using final demands as opposed to outputs, we are actually capturing all of the intermediate transactions of the economy. It's capturing all of those things. So this is the PPF. 0 is greater than or equal to f of y, j, t. Final demand. Factors. Primary factors, okay? Not intermediate factors, not intermediate inputs. This thing is a summary of what the economy can produce given all the intermediate transactions. So this takes into account all the intermediate transactions that occur across industries. So this takes into account all the intermediate transactions. So this is, when we did that problem, remember the couple of problems I had where you had this sector X and Y and a sector Z, you were essentially calculating this final thing once you incorporate all the X and Y's into Z.
How do we do that to VA? Can I say that the summation of all VA is equal to GDP?
So
Of all sectors, I mean VAI, PVA, VAI is equal to GDP if I aggregate them out.
yeah, we have that summation value added, PVA, VAI,
Yeah.
summation PVAI value added I. summation across I, P, I, Y, I. Final demands equals incomes. Value added equals final demand equals incomes. Okay. Then, just to complete, GTFP, this was the PPF approach. Sum of sectors approach. GTFP is summation across I, QI over GDP, GTFPI. TFP in sector I. The two are equal. So the sum of sectors approach equals the PBF approach. Sum of sectors equals PBF approach. They're the same. One thing I don't recommend is a lot of you are looking at the original definition of TFP and saying, oh, it's minus lambda DFDT over GDP. Okay? Or if you remember that from the derivation of the thing. That's not the best way to proceed because in the real world you don't typically see DFDT, you see these things. You see the expenditure shares, etc. You don't see DFDT. So the idea is these formulas are allowing you to intuit or to find out what minus lambda DFDT is over GDP. And furthermore, if you do minus lambda DFDT over GDP, you have to figure out what lambda is in that problem. It all gets complicated. So this is the formulas you should be using, not this original idea of what TFP is. Sabrina?
What's the GTFP in sector I? Is it GTFPQ or GTFP value add?
Very good. This is GTFP sector I, gross output. It's the gross output approach, not value-added TFP. There is an additional measure which we could have done the value-added, in which case it would have been the value-added weighted share sum of sectoral and value-added TFP growth rates. Right? We have a third calculation. Any questions, or should I let that on as well? Any questions about this? So this here is a multiple, and that comes from the idea that the way to intuit this, and the way to intuit all things at TFP is basically a B, is to generate income for the factors of production. And we have the technological derivations of TFP growth, and then we saw at various points that TFP was related to how much the income of each factor of production was rising, or could rise. I can go down that route, or I can take some other questions. You guys can.
For example, GTFP.
Sure, whatever you like.
About the very first chapter, the Gershon from and all the homothetic utility functions. If I'm correct, homothetic utility function is just like a more general formulation of a homogeneous of degree 1 utility function. So every homogeneous of degree 1 utility function is homothetic, right?
That's correct. Every homogeneous degree 1 function is homothetic, exactly.
And then we have that speciality of homothetic functions, that it has no elasticity, that the elasticity of income is everywhere 1. So from each regulator from the origin, you get the same share of demands in goods.
Yes.
So what's the speciality about homogeneous utility functions? If that homothetic utility function is already that special, what is it that makes homogeneous functions different from homothetic function interpretation?
What's the difference between homogeneity and homotheticity?
I mean, I know it in math formulation, but what does it mean in interpretation if the homotheticity is already that special and that, I mean, it's really not, yeah.
So if effectively, the only reason why we don't go with homogeneity of degree 1 when we write down the utility function is because the utility function should not have any cardinalities, so we don't really care about its numerical value.
Okay.
So, given that we don't want to impose it as any kind of numerical characteristics, we don't impose homogeneity of degree 1. It's just essentially some transformation. But having said that, it could clearly just as easily be homogeneous of degree 1.
Okay.
Because since we don't really care about, you can take this cardinality two ways. Say, on one hand, ooh, we can't impose any kind of cardinality on this problem because utility measures order, it doesn't measure value. On the other hand, given that you don't really care at the end of the day about value, you could just as easily say it's homogeneous to degree 1. And in fact, if you look at most of the utility functions that we write down, when we write down these homothetic utility functions, we write them down as homogeneous to degree 1. Because, what the hell, why not? It doesn't make any difference anyway. And in fact, if you read Neary's article, Neary ends up saying something like, well, if it's homothetic, E of PU equals U E of P. Okay? He does something like this. Well, actually, that's actually only true if it's homogeneous to degree 1. Then it has this characteristic. The amount of expenditure required to attain the level of utility is linearly increasing the level of utility. Because you can think, if you drew this thing here, and if these things were literally homogeneous to degree 1, so that a doubling of x of y and x double utility, then you could see that to get double utility, I'd have to double my expenditure for given prices. So he starts making these appeals. But basically, the answer to your point is it's a combination of bizarre handling. We don't really want to impose any kind of homogeneity of degree 1 on utility functions, because we want to allow that you can make any kind of transformation. You can call this 10 and this 20, or you can call this 10 and you can call this 100, and we shouldn't care. But at the same time, given that we only care about their ranking anyway, why don't we just change units so that it's all homogeneous to degree 1? In practice, that's what we actually end up doing. So, it's quite similar. It's extremely similar, except to the degree that it's homothetic when we don't want to make a claim that we actually know the cardinality.
So the point is that dealing with utility, we want to keep it very general, which is different, whereas in production function we need homogeneity because there it matters for the production function, right?
In the production function,
Yeah.
we have a statement. It's
Exactly,
something
exactly.
real, observable.
Yeah. So that's the difference, that you want to keep it general in the utility function.
Yeah, so we're going to keep it general. The production function, we feel, is something real that we're referring to.
Can you explain about the problem set, the assignment, we'll see about the current value close state of the car and classify the evolution of E and P?
Sure.
Yeah.
So, so first of all, just the words, okay? First of all, just the words. You mean the explosive path?
Yes,
okay? The key thing here is that Q is 1 over 2u. Right? Now, let's think about a path like this. E to the alpha is how E's productivity. Minus u squared is the cost of consumption. As Q is rising, the marginal cost of consumption is rising. As U is going up. Because E dot is E to the alpha minus U squared. And you can think of this as the cost of consumption. I'm being loose here, okay? It's the cost of consumption in terms of the resource. And along this path, the marginal cost is 2u. And as u increases, the marginal cost increases. And this is, you can think of production. Just think intuitively, okay? And therefore, the marginal product of E in production is alpha E to the alpha minus 1. And as E increases, as E decreases, this increases. So, if you think about this path, there's something completely bizarre about this path. Along this path, U is rising, so the marginal cost of consumption is rising. E is falling, so the marginal product of E in production is rising. But instead of trying to conserve E and build E up and cut back U, we do the opposite. We keep on consuming more and more and drive E down to 0. Why? Because what's happening on this path is that Q is falling. So there's a capital loss, period by period, that's justifying this bizarre behavior. Q's not going to be E's not going to be worth anything tomorrow, so just throw it away. Might as well eat it up. Along this path, we have U is falling, so the marginal cost of consumption is falling. E is rising, so the marginal benefit of having E is falling. So why are we accumulating more and more E? Well, because Q is 1 over 2U. So as U is falling, Q is exploding, and capital will be worth so much tomorrow, E will be worth so much tomorrow, that we try to conserve it more today. Moment by moment along these paths, there's a capital arbitrage condition that's being met, but the whole path doesn't make sense. I can go into more detail on that. First, if there's any questions about the intuition, then I can go into more detail. So, first of all, just a reference to an equation we've seen before. R is equal to pi over V plus Q dot plus V dot over V. Right? The value, the return, the intertemporal return, the rate of return, the intertemporal rate of return, right? This is what you're earning through time. It's equal to profits over value plus capital gains. And we use this, you're not being examined on it, but of course we used it just now in the dynamic model of innovation. Made reference and stuff like this. Okay? And in this problem, every economics optimization problem has a capital condition like this. There's an arbitrage condition that says that this must hold. Let's actually integrate this equation. So let's integrate this equation. Let me multiply both sides. VR plus V dot equals pi. So I want you to understand, when I'm talking about pi here, I'm talking loosely. I just mean the dividend, the benefit, okay? The payoff, all right? We're not talking profits per se, it's just the payoff, all right? And V is the value of the asset, all right? If you take this equation, did I do that right? No, I didn't do it right. Minus V dot. I multiply both sides by e to the minus RT. Okay? Then I realize that this is V e to the minus RT dot. Okay? Now I integrate. I'm going to integrate from V infinity to T, V e to the minus RS ds dot, to the integral from infinity to T, pi of S, e to the minus RS ds. This thing here is V of T, e to the minus RT, minus V infinity, I'm just using infinity instead of writing limit, e to the minus R infinity, and it's equal to I'm sorry. You change both sides here. The integration just didn't actually happen. Couldn't happen. So I needed to do this. Now I think I'm okay. Yes. Now I'm okay. Right. Sorry about that. Okay. So now I'm back on track. I just realized that when I told you this was this, it was just not true. It was all just a lie. I had the other signs changed. And then this is equal to here, T to infinity, pi ds, e to the minus rs ds. I changed the direction of the equation from infinity to T to integration from T to infinity. Okay? So now, what do? Let's multiply everything through by Vt, by e to the RT. We have Vt is equal to the integral T to the infinity, pi of s, e to the minus r, s minus t ds, plus V infinity, e to the minus r infinity, e to the RT. Okay? Now this is what we want. That's what we actually want. We want the value of the asset to equal the net present value of its dividends. But for that to be true, we need this equal to 0, question mark. Okay? For the value of the asset to be the net present value of its dividends, this limit has to be 0. Now, so the point I'm trying to make is, R equal pi over V plus V dot over V. This implies that V of t is equal to integral t to infinity pi of s e to the minus r s minus t ds plus this limit as t goes to infinity of V of t as x goes to infinity of V of x e to the minus rx e to the rt. And we want this to be equal to 0. Now, by the way, this equation implies this. If you differentiate this, you get this. Okay, so differential equations have a solution whose solution depends upon an initial condition, right? If I take a derivative of this differential equation, this is always true. This always goes true. I always take a derivative of this with respect to t, I always get this. But from here to here, I need to have this condition. And this condition is actually related to the transversality condition. It's related to the fact that along the correct path, this condition holds. This is true. The value of the asset equals its net present value of its dividends on the saddle path. On the explosive paths, this thing does not equal 0. The value of the asset does not equal the net present value of its dividends. Is that clear or is that muddy? Let me add one further thing if I can. Lambda dot equals minus HE, right? Q is equal to e to the RT lambda. Q dot equals R e to the RT lambda plus e to the RT lambda dot. Q dot is equal to RQ minus e to the RT HE. H tilde is equal to e to the RT H. So we have Q dot is RQ minus H tilde E. Or R is equal to H tilde E over Q plus Q dot over Q. Q equals value. H tilde E equals dividend. Q dot over Q is capital gains. The necessary condition for an optimal control path is an arbitrage condition, that the flow of dividends over value plus capital gains equals R. And every point along these paths, this is true. This is constantly true at every path. This capital gains, this arbitrage condition, this capital condition is holding. But only on this path is it actually true that the value equals the net present value of profits. Because this limit condition is related to the transversality. I haven't gone all the way to proving it, but all the types of problems that we're relating to are related. Any questions? Is that unclear? Or do you have more explanation, or is there something else you'd like me to talk about? So, how do you answer a question where you're asked, discuss an explosive path? Identify how the current value co-state relates to what's on the diagram. The diagram may not have Q on the axes, because you might be solving a standard, say, C versus K problem, or here U versus E problem. Identify how your current value co-state relates to the diagram. In this case, it's inversely related to U. Then what has to be happening along the explosive path is capital gains or capital losses, Q dot over Q, are justifying what seems like bizarre behavior moment by moment. So along the explosive path, Q dot over Q has values that justify this apparent lunatic behavior. So here, We're spending more and more on U, we're reducing E further and further, and that's because Q dot over Q is negative, so the capital loss convinces us to do it. So these explosive paths have that characteristic, but only along the saddle path is it the case that Q is properly valued so it's equal to the net present value of its dividends, the net present value of the benefits coming from Q. So you need to just identify what the co-state is. A little bit more on the co-states. Lambda, the regular co-state, is the value of having more of this K to the beginning of the problem. So lambda t, if the problem started at time 0, lambda t is the value of having more K at time t, or more E at time t, but evaluated from the point of view of time 0, at the beginning. If you told me at time 0 that I was going to give you more K at time t, what's it worth to you at time 0? Q, the current value co-state. Well, mechanically it's just e to the r t times lambda t. Intuitively what Q is imagine you take any optimal control problem from 0 to infinity. Imagine you run it for 3 days, and then I wake you up on day 3 and restart the problem. Or I wake you up on day 5 and restart the problem. I wake you up on day t and restart the problem. So in your mind, you can think of the following exercise. If I had an optimal control problem, and I planned it all out, and then I was woken up at time t, and you said, we're restarting the whole problem. Well, of course, given my plan from time 0 to t, my plan from t to infinity will be the same. Nothing's changed. But that qt will be the value of having more capital on that day. Qt is if I woke you up at time t and said, we're restarting the whole program, and starting from now, what's the value of you to having more capital right now? On this day t. So again, lambda is the value to the beginning of the problem of having more of this resource at any point in time. The current value co-state is e to the rt lambda, this q, is the value to having more capital on that day as if you restarted the whole program on that day.
So the part I don't get about the explanation of intuition is why does the program have to be restarted? So why don't we just look at
Because the intuition is, I'm imagining myself living this life. I'm living this life, and every day as I'm living this life, I have the choice to change what I'm doing. But I don't. I keep living this life as I'm moving along because this Q is doing this thing to me. This Q is the price of capital. I'm living this path. And every day I wake up and say, why don't I do something different? Oh no, because I expect this path to continue like this capital.
So is the difference just that at the time where it's being evaluated of having more K? So is lambda evaluated at time 0, but Q is evaluated at that moment?
At that moment. That's all it is. The difference is just the value of having more K changing when your value is.
Okay, but I see how Q, for example, evolves on that path. But when you said about restarting the program, doesn't the development principle of optimality, doesn't it just work like that? That if you interrupted the program at some point t and you gave the possibility to reprogram it, then you would still do exactly the same.
Exactly.
So it cannot change anything in your choice variables. It's only the perception of the price.
It's just not the perception, it's the value of the problem.
Yeah.
So one is, let's write this down formally. So V of 0 is integral 0 to infinity e minus r u, etc., etc. And lambda of t is dv 0 dkt, right? And v of t is the integral from t to infinity of e to the minus rt. And qt equals dvt dkt. I wake up at time t and I start the program. And of course, you're right that if nothing's changed in the world, then this is the same program as I had there.
Yeah.
As long as nothing's changed.
I have another
question related to the last year exam, the first one question, the last part. When the depreciation rate increases, this curve shifts down. However, in that case, in that point, in that previous steady state, we are in the quadrant where there is an explosive path for this diagram. So why it is that we instantly go back to go to the new steady state? Why just don't follow the explosive path in the quadrant?
Okay, so Wallace is referring to the problem from last year's final, which you've seen it, but it's another one of these maximize things, except this time there's a E appears in the utility function as well. I'm not going to go through the whole thing because I'm going to focus on what he's asking. What he's asking is, in the problem, I say, okay, solve the problem, and you solve it, and you get the usual thing. Saddle path, you're going to look at these things. And then suddenly I decided to throw something extra in the problem and said, okay, now imagine you wake up one morning and delta, which is one of the parameters, has changed. And when you wake up one morning and delta has changed, the new diagram looks like these solid lines. So this is the old diagram, the dashed lines, and now the new diagram is the solid lines. Okay, so this is why I was talking about nothing has changed. If you have an optimal control program, you design the problem, and you start going along your saddle path. That is optimal control. The way we've done it is deterministic. Nothing's changing. Then you wake up one morning, and the world has changed. So what do? You re-optimize. So the key thing is, in a typical optimal control problem, this goes back to the solution of an optimal control problem. On the horizontal axis, we typically put a state. On the vertical axis is a control. I am free to set the control at any point in time. Of course, if nothing changes, I'll just follow the pattern I came up with. But if I wake up one morning and the world has changed, then what I do is I re-optimize.
So, with my idea, I just wasn't sure that, yeah, so because the E is at the same level, and we are free to choose the control variable, we just choose it to be to get the new steady state.
Yes, so let me do a general thing, and then let me talk about the problem, the specific problem. So generally, so just imagine I've got this. Imagine that's just the kind of problem I've got, okay? And I start you off here. Well, then you go there, right? And you start traveling along and traveling along because you expect the world to be the same forever. And then you wake up one morning and the world's changed. And let's say now it's down here. And I got a new path over here. Then what I do is I wake up and I jump. Right? Because I wake up in the morning, if I follow this path, I'm exploding off to nowhere. This is not the solution any longer to the problem. I wake up and I solve the problem and I jump. So whenever you're calculating a solution to an optimal control problem, you're saying, given all these characteristics of the problem, what's my best solution? But if I suddenly change the characteristics of the problem, you'll change the solution. So if I'm traveling along this path and suddenly I wake up and I find that this is the path, then what I'll do is I'll lower the control, because this is a jump and this is not. This doesn't jump, this evolves. In the particular problem, in last year's final, you're at here, and the new steady state is right below you. So you just drop your control and you let it steady state. There's nothing to evolve. But this is why it's important to understand what an optimal control problem is every time. Given the current state of the universe, you're picking an initial value of your control, and then following the path unless things change. And there are versions of optimal control, like stochastic optimal control, where we include the uncertainty, etc., etc. We don't do that. Anything else? remarks? Any other questions? Yes.
Regarding this, if I look at the equations for Zoloki, E dot will depend on R as well, so I can really see if we're jumping and changing the R, I mean R is changing like the control. So why doesn't the locus become positive, I think in this case, of E? So I don't get why E isn't changing if the locus is positive.
In this case, we are dividing both equations with the same number, both curves. That's why they shift down proportionally.
Yes, they both shift down proportionally in this case, but I think he's wondering, so the control variable in that problem, R, was something like C over E, right?
Yep.
So what you think about this is, you're not jumping E when you're jumping R. You're jumping C, right? You don't jump the E. You're only controlling C. Is that okay?
Yeah.
Always keep in mind, don't ever forget this, the position of these loci in the space does not depend upon your current E or K, whatever. They're determined by parameters. Your position, you draw these curves for any notional combination of these two variables, and then you find out where you are in that space. Your position in that space doesn't change the curves. Right? Curves are just these combinations of these variables.
Tree question 6, maybe the Uzawa theorem one.
Can we do what is on Steve?
Tree question 6, maybe the Uzawa theorem one.
Okay, which question 6 and which problem?
Tree. Problem 3. Concept 3. Question 6.
Yeah, okay, the A, B, and D question, the CES A, B, and D question. Do you remember that one? CES production function with an A on the outside and a B and a... You just show it to me, I'll just put it on you. This question. Remember? A, B, and D. Okay? With CS? And you're wondering the intuition part about that? Is that what you're asking about? So, actually, several questions. Actually, one student asked me, how do you know in this problem he said that EL was equal to 1 minus EK? You could actually just calculate that out, but if it's constant in terms of scale, the sum of elasticities in all factors will equal 1. It's something you can always rely on. It's homogeneous in degree 1. So it's got KL and M, and EK plus EL plus EM equals 1 if it's homogeneous in degree 1. Right? But I don't think that's what you're asking. You're wondering about Uzawa's theorem, the use of Uzawa's theorem. So, Uzawa's theorem, you want to remember the following facts. We take A and B as given. K dot is Y minus C minus delta K. B, F homogeneous in degree 1. And then we have 3 propositions or facts. Gy is greater than 0, gk greater than 0, gc greater than 0. Then we have number 2. Gy equals gk equals gc. And then we have number 3. Harrod neutral technical change. Now Uzawa's theorem is 1 plus A, we always assume A is true, implies 2. But if they're all positive, Gy is positive, gk is positive, gc is positive, and we have this, then we'll get 2. And then the second part of Rosales' theorem is that 2 plus b implies 3. I've drawn the circles inside each other because if they're all positive and A holds, then they're all equal. But of course they could all be equal and negative. So that's why 2 lies outside 1. If they're all equal, positive or negative, then 3, para-neutral technical change. They don't have to necessarily be positive. Para-neutral technical change lies outside all of these because you could have para-neutral technical change and not have constant growth rates or equal growth rates or anything like that, right? You don't have to be on any kind of steady constant growth path or balanced growth path. Now the problem was y is equal to a f of bk dl. Well, given 2, I know it's got to have a para-neutral technical change. So given 2, I know 3. Okay, I know 3 must be true. So therefore what I've got is y is equal to AB f of k d over dl. I knew I had to get to something like that. And then I have to make this a constant. I need to get rid of it. So you use your intuition to let you know where you're going. And then then it's easy. Once you know where you're going. What we have is sets of, every area we've done, there's very simple intuition associated with each thing. Consumption, Gershon-Grahn, production, Gershon-Grahn, homotheticity, non-homotheticity, when it holds, when it doesn't hold, indices and so forth. Solo growth model, capital labor ratios, etc., two-factor version models. Each of these things, you have some sort of simple ideas in your mind, this is how it works. And then you got to have the tools along with it that can make it work when you get the problem. So how to do an optimal control problem, how to handle this other thing. But knowing where you're going helps a lot. Just having the broad picture, so just having a sense of what the whole thing looks like helps a lot. Anything else? Yes.
For the measurement chapter, could you please explain again about when we compare poor countries with rich countries, and we say that last period price index overstates inflation. Therefore, we see that poor countries better when we look at rich countries' price.
Right, so Laspierre's price index always overstates inflation because it doesn't take into account substitution that occurs.
So what's the red measure for inflation? If Laspierre price index overstates?
And the Pasch understates. The right measure would be if you actually knew what the utility function is. If you knew the actual utility function, you can answer the question, how much do I have to increase the income to do the other guy's utility at your prices or his price? And you can answer these kind of questions, you get real quantity indices and you get the inflation. So the key thing is this, that we observe M final and M base. And we want to break that down into a quantity index times a price index, right? That's essentially what we're going to do. We're going to take the ratio of nominal expenditures and break it down into a quantity and a price index. And the quantity index, first of all, is not unique unless you have homothetic utility. Otherwise, depending on how you define the quantity index, it changes. But when it's unique, when you have homothetic utility, there is a unique quantity index, means that if I ask you how much do I have to increase M's income to allow them to enjoy finals utility, at base income to enjoy finals utility at basis prices, or how much I have to cut finals income to allow them to enjoy basis utility at finals prices, that has the same answer when you have homothetic utility. And then there's a unique price index. So the point of the price index is to recover the how much of this is nominal and how much is real. But if you don't know the utility function, you don't know what it is. So we just pick things. Laspierre's overstates, Pasch understates, it's somewhere in between. If you knew the utility function, you can calculate this, what we did with the Cobb-Douglas case. And so when we're doing dependable tables, we're just using one particular price index. I probably need to quit now because we have other people coming in. So if you want to stay on and ask more questions later on, you're welcome to. Now these notes, if you want them, you're welcome to take them. So anybody who wants these, or wants to share them between you, wants to do anything with them, you can or not, it's up to you. Okay, just-